On example number 5 in your book, the work does leave out a few of the steps because they're using a calculator to evaluate it. I'll go through the steps with you. You're given this function and you're asked to evaluate it using the 3 techniques. So on the previous page, they give you the 3 techniques for the left endpoint, right Riemann sum, and the midpoint of the Riemann sum. And that's not really where they leave it out. Where they leave it out is going into this summation here. So the width of each rectangle here is going to be the length of the interval divided by n, so b minus a over n, and you get 1 over 25. The value for your x sub k using the left, right, or midpoint using those formulas is be plugged into here. So we go ahead and plug in the k minus 1 times the delta x. We get this 1 over 25k minus 1 over 25. And using the formula, we're plugging in the value of the function. We're plugging in the x sub k point into the value of the function. That's going to give us the height of the rectangle. When we multiply it by the width of the rectangle, that gives us the area of that rectangle. And your book doesn't really show you what's going on here, so I'm going to show you the math. It's not very pretty because of the 1 over 25, but really we have 1 over 25k minus 1 over 25 to the third power minus 1 over 25 all times 1 over 25. We're going to take the summation of k equals 1 to 50. So I'm going to have to expand this out, and I'm going to be kind of do some tricks with algebra to make it a little easier, so I'm going to rewrite that over here. I have the summation k equals 1 to 50 of, what do I have, 1 over 25 k minus 1 over 25 to the third power minus 1 over 25, all multiplied by 1 over 25. So just kind of doing some algebra, I'm going to pull out a 1 over 25, so I'm going to have my k minus 1 cubed. When I pull out a 1 over 25, I also have to pull out the 1 over 25 cubed. So everything's legit. Minus 1 over 25 times 21 over 25. So there's a lot of things going on here. To make my life a little easier, I'm going to write this as, sorry, I made an error there. It should be, this should be minus 1, not 1 over 25. So minus 1 because of, ooh, it's actually plus 1. So I'm glad I looked at that. Plus 1. So this is going to be plus 1. This is going to be plus 1. Right? Because I'm plugging in my x sub k point cubed plus 1. This is what my x sub k point is. I'm going to pull out 1 over 25, and then I have k minus 1 cubed, because I'm left with k minus 1 cubed. To make my life easier here, I'm going to write this as 25 over 25 cubed. That is 1. So I could pull out this 25 cubed in this group, and I'm left with 1 over 25 k minus 1, still cubed, plus, in this case, 25 cubed. And then that's still all being multiplied by 1 over 25. So the algebra here, I pulled out, oops, that's going to be the 1 over 25, so I could loop it with this 1 over 25 cubed. So I wrote this as 25 over 25 cubed. I pulled out the 1 over 25 cubed and just put it here, so then I can put the brackets like this. Now, essentially what I have here is I have a cubed times b times a. So I could write that as a to the 4th times b, and that's kind of what I wrote. So I'm just going to write the summation of k equals 1 to 50 of 1 over 25 to the 4th power. Then I have k minus 1 cubed, and if I plug that, if I expand that, that would be k cubed minus 3k squared plus 3k minus 1. And then I have, sorry, oops, minus 1 plus the 25 cubed. So I pulled out the 1 over 25 and grouped it with 1 over 25 cubed to get 1 over 25 to the fourth. I expanded my k minus 1 cubed, and I got k cubed minus 3k squared plus 3k minus 1. And then I added my 25 cubed, so add 25 cubed. I can simplify it one more step. 25 cubed minus 1 is just a constant, and I can do that real quick. 25 cubed minus 1. And I would get 15624. That would be a number that I add into that. So now at this point, I'm going to use the theorem 5.1 when I'm adding a constant. K goes from 1 to n. Of a constant is going to be a constant times n. With k goes from 1 to n of k, I use this formula, k squared this formula, k1 this formula. So I'm not going to do that on these because it's kind of time consuming. The constant can come out front. So when I actually sum this, k cubed, the n is 50. So if I want to sum k cubed, I'm going to use this formula with n is 50. And if you do that, you end up with write this, I have 1 over 25 to the fourth power times, if I plug in 50 squared times 51 squared over 4, I end up with 1625625 minus 3 times k squared. So I'm going to use the k squared formula with n is 50, and I do that, and I end up with 42925 plus 3, the k formula, n times n plus 1 over 2, so 50 times 51 over 2. And I end up with 1,275 minus, or sorry, in this case, plus this constant, 15624. But when I sum a constant from 1 to n, when I sum a constant from 1 to n, I take that constant times n. So this is actually going to be multiplied by 50. So doing this math, very long way to go about it. Plugging this in my calculator, you should get 5.8416, which is what they say. Going back, they just didn't show you that calculation. Doing the same thing here, you're only plugging in 1 over 25k, so it makes it a little easier. To simplify that, you don't have as many terms. And then, of course, this midpoint one, you're going to have the same amount of terms, just a little bit different coefficients. On the homework problem, it's a little easier because it's just to the first power. So I go through and I find the length of the length of each rectangle, which is 2 over 25, using the right endpoint. So I'm using this formula here. So again, it's a little easier because I only have one term here. I'm plugging that back into the function, so I have 2 over 25k plus 1 times my length of my rectangle. So I distributed this in here. So I have 4 over 625k plus 2 over 25. Using the theorem to sum k, the sum from 1 to 50 of k, I use that formula, plug that in, multiply by the coefficient, plus the formula of a constant, would just be that constant times n, in this case n is 50, add that together, and you would get the approximate area. These are really algebra problems. They're not calculus problems. There's no calculus involved. This whole section is kind of leading up to pushing the integral and replacing this integral with this summation with an integral. So really, I don't foresee any of these on the final exam, or honestly on exam 4, just because the ideas leading up to calculus is really algebra. It's all algebra, and sometimes the algebra is tedious and annoying, but it's getting us closer and closer. We're getting closer and closer to approximate the integral, and eventually if we take the limit as n goes to infinity, we're going to be able to switch out the summation with the integral sign and do calculus. So hopefully, you know, you find this section somewhat beneficial to the idea of what an area is. Don't get too caught up on the tediness, how tedious it is. I don't expect a problem like this. Definitely not on exam 4, and I'd be really surprised to see it on the final. Please keep me posted if you have any other questions. Hopefully this helps answer them. Best of luck.